Today's presentation, as the slide indicates, is a history of quantum mechanics, the very early history of quantum mechanics. And I am doing this on the occasion of World Quantum Day. And I put the website there that people can go to learn about this. It's done on April the 14th, and that's a reference to 4.14, which is a rounding of Planck's constant. It is intended to be actually a quantum mechanic week where they pair teachers and scientists to do presentations in the primary and secondary schools. It's very decentralized. It's just something that people will do if they have interest. And as I indicated, if you go to the website, you'll see that there is quite a lot of activity in Europe, but as it happens, not all that much in the United States. Oh, and by the way, I sort of plan to talk for around 30 minutes, maybe 40 minutes, and then turn it over to comments from the people here present, because I know a number of you are scientists that will have their own insights about the development of quantum mechanics and the applications. And also, that is generally about the time that my voice fades away. So that's our plan. The agenda will cover some of the major milestones, all of which mostly were in the first third of the 1900s. And you can see them listed here. And, you know, historically, it started as a recognition of the inadequacy of classical view in the years leading up to 1900. And the development over the period from 1900 through the close of the Second War, of course, was hampered by those wars. And we're going to look at some of the insights that took place in that period. So, before 1900, the universe was a clockwork, and that's been pointed out by many people. The governing laws, they had definite, unique solutions. If you knew the present, you completely understood the future and the past. Now that is kind of disturbing if you're interested in questions of free will and consciousness, but nonetheless, that's the way that Western European scientists viewed it. It was logical and perhaps even comforting to them. And the laws of thermodynamics and electrodynamics, they were real triumphs, you know, for the 19th century. But the underlying phenomena of those laws was not at all clear. They knew of the electron as a particle. They understood electromagnetic radiation as waves. And the existence of atoms was widely accepted. But there were observational flaws. Spectroscopy had been available from the early 1800s, and we knew that when you heat materials to a given temperature, they have a characteristic glowing color. You also saw completely unexplained emission and absorption lines. Problem is that when you use the laws of thermodynamics, you tried to calculate the emission energy for different wavelengths of light, the behavior was observationally wrong. The calculations indicated that the emission strength should increase without limit as you went to shorter wavelengths. And that was called the ultraviolet catastrophe. It simply was a case where the beautiful laws of thermodynamics simply did not seem to correctly apply. Max Planck Started working on that problem around 1894, and he struggled with it for 6 years. And he finally had an insight that is the birth of quantum mechanics. Uh, Let me just go to the next slide here. In the spectrum you see on the right, you can see that the classical theory predicts a curve that should just go up and up without limit. And then the actual observations go up to a peak and then rapidly decline. Okay. So to solve the problem in 1900, October 19th, in fact, of 1900, he introduced the idea that energy is quantized and that this means that only certain energies would be allowed. Uh, he referred to the discrete packets of energy as quanta, giving quantum mechanics its name. Now, this is a major departure, going from the classical physics of continuous phenomena to one of quantized phenomena. He developed his famous constant, which was, basically observational, adjusted to get the curves to fit. And he admitted that he had no explanation for the new formula. It simply fit the data very well. He also said that classical mechanics was still correct, providing that only integer multiple values of physical quanta were allowed for any given physical property. So they were sticking with their classical view, just saying, well, we have piano keys now, and things like energy, magnetism, and so forth are played with piano keys and not with continuous values. Physicists had to guess what the given quantum might be. This was not done by a calculation. You simply looked at a phenomenon and he said, well, the quantum for this must be this value. Then in 1905, Albert Einstein became 26 years old and changed everything. In 1905, he expanded on Planck's ideas by applying the concept of quantization to light. Now, this is a little bit different. He proposed that light itself would be described as particles, later called photons, in addition to waves. This is different from just having energy levels described by quanta. He was holding the carrier light itself is quanta. Isaac Newton had suggested that light could be particles, but the wave phenomena based on Christian Huygens' observations, the Young experiment, and Maxwell's equations was the dominant theory, that light had to be a wave. Waves of what? Well, they weren't too sure, but definitely waves. And this explanation was crucial to understanding the photoelectric effect, where light on a metal surface ejects electrons. Einstein's work provided strong evidence for the duality of light as waves or particles, depending upon the observational circumstances. Some years later, 1921, the Nobel Prize was awarded to Einstein in recognition of this result. Also in 1905, Ernest Rutherford, who was 16 years older than the young Einstein, conducted experiments that revealed atoms' internal structure, that it had to have a nucleus. Niels Bohr, who was a youngster in Rutherford's laboratory, introduced quantumization ideas for the hydrogen atom. And having done that, he found that he could explain the emission lines of hydrogen. It's worth noting, though, that while it was very successful for hydrogen, it was not successful for heavier items, such as helium. There was a helium problem. They called it the helium problem. It considerably strengthened the quantum theory of the time, which we refer to now as the old quantum theory. In 1915, William Wilson, who was age 40, considered the effect of energy quantization on position and speed. Sommerfeld continued that particular work. Niels Bohr introduced a model of the atom in 1913, which incorporated quantum theory to explain the behavior of electrons in atoms. Now you can see my little chart of the evolution of the concept of the atom here. Let's see, starting with Democritus, where it was simply little blocks of stuff. John Dalton, and then we have the pudding model that, let's see, came from Thomson. Rutherford that cleaned it up a little bit by giving a organized orbit around the nucleus. Niels Bohr that gave us orbital levels. And finally, Louis Borlase and Edwin Schrodinger's atom that had probabilistic clouds. Now, this model was very good I said, explaining the emission of lines, the emission lines. But it did have some flaws. And these flaws is that the idea of sharp orbits for electrons, well, the orbits, they should decay. You know, as orbiting electrons should generate electromagnetic radiation, which they did not. And it was not explaining larger atoms. It was not providing an angular momentum of 0. These were all flaws that Bohr recognized. Okay, I should also mention the Zeeman effect. They knew that the spectral lines split when atoms are in a magnetic field. Okay, Max Born. At Göttingen, we also took part in the attempts to distill the known mechanics of the atoms out of experimental results. The art of guessing correct formulas was brought to considerable perfection. And I think by that he means that it was unsatisfactory that you could explain stuff with quantum, but you had to do it by basically fiddling with the formula values until you got something that fit the data. Werner Heisenberg, who was 23 at this time, was particularly good at producing tables of these allowed physical quantities, basically the guesses of the values that made it all work. De Broglie hypothesis, 1924, was that the wave-particle duality extended to matter. That matter itself could be associated with a wave-like behavior and have a wavelength associated with it. And that became our conceptual foundation for wave mechanics. Okay, this is kind of interesting. 1925, Heisenberg had allergies. And springtime in Göttingen was not a good place to be if you had allergies. He was in Max Born's laboratory, and Born allowed him to take a vacation in the North Sea island of Helgoland. Well, that helped matters. His allergies decreased, at least in their effect, and he turned his mind toward physics and organized the physical properties that he had discovered and put it into a matrix that was related to the old quantum mechanical rules. Let's see here. Moving on. Okay, so the matrix mechanics, that was developed by Heisenberg, Max Born, and Jordan. They also brought in the uncertainty principle at that time and began putting the old classical ideas to rest altogether and moving toward the idea of quantum mechanics as being a true picture of the universe. It's worth noting that they were not making a decision about whether matter was really waves or particles. They simply focused on what they could calculate. And now many decades later, we have this shut up and calculate attitude toward quantum mechanics in some quarters. So here were the principles of the quantum matrix mechanics. Zero properties are quantized. The physical state does not assign definite values. Measurement creates a definite value, or rather pulls it out. You really can't make any statements until measurements are done. It's non-commutative. By that we mean the order of measurements for several properties will affect the values that you get. And finally, if the Planck constant is set to zero, the equations degrade gracefully down to their classical equivalents. See, this is a quick diagram of how the Dirac bracket notation worked, but I won't go through that. Let's talk next about the Schrodinger wave mechanics. Now, this was independent of the other work in the Christmas of 1925 and published in 26. He came up with a wave function to produce probability amplitudes. He also came up with the idea of superposition of states, and this he offered as an alternative to matrix mechanics. Now, later on, the matrix mechanics and wave equations were shown to be equivalent. However, at that time, at least for that first year, there was quite a controversy over it. You see, the Schrodinger equation was a familiar mathematical form. It looked very similar to equations that had been used in classical physics, whereas the matrix mechanics, it was all new notation and methods. So the Schrodinger equation was greatly favored initially. Schrodinger was discouraged, if not repelled, by matrix mechanics. He just didn't like it. And Heisenberg, on his part, was quite forceful in how he found the Schrodinger equation to be detestable. So they were quite at odds over the issue. However, in 1926, and working independently, it should be remarked, Schrodinger and Karl Eckart of Caltech showed these differences were superficial. So Schrodinger himself showed that his equation was equivalent to matrix mechanics and vice versa. And we also had the same result from Eckart at Caltech. And it's interesting that it was Caltech because up to now you would have the impression that the entire development of physics was taking place over in Europe, but at least there was a guy at Caltech working on it too. Next, I'll come to the Soive conferences. This was instituted by Belgian industrialist Ernest Soive and it's supported by the King of Belgium. The first conference was in 1911, and you can see that it included the various luminaries of that time. However, World War II kind of interfered with the conferences. So the second, third, and fourth were not that much to speak of. And in fact, the fourth was held without inviting many of the more important scientists of the time because of the political differences of the nations. And someone is moving my laser pointer around. I don't know why you're doing that. But the fifth conference was in 1927, and that's the really important one. And you can see the names that were in there, particularly Schrodinger and Einstein. So Einstein and Bohr dominated that conference. Einstein was very disturbed by the probabilistic nature of the Schrodinger equation and of matrix mechanics. And paraphrasing his statement on that, he said that God does not play dice. That was not his exact words, but that was the idea that he had. Niels Bohr, and this is his exact quote, was stop telling God how to behave. So Einstein wanted to show that quantum mechanics uncertainty was not rational. Each day of the conference, he would propose a new thought experiment that would contradict quantum mechanics. And Niels Bohr would consider it overnight and come back the next morning with rebuttal. It was said that each afternoon he would be wandering around muttering, Einstein, Einstein, because he felt so badly under attack by all of these thought experiments. Anyway, that debate between Einstein and Bohr dominated the conference, and it continued for years afterwards. Out of that conference came the Copenhagen interpretation. It was primarily developed by Bohr and Heisenberg, and it posits that quantum mechanical particles don't have definite properties until observed, and that quantum mechanics can only predict probabilities. And that interpretation is our influential but controversial one. It's worth noting there is really no definitive statement of the Copenhagen interpretation. The principles you see on this slide are the ones that are taken to be core to the concept, especially the Born rule that the wave function of a system yields probabilities for the outcome of measurements of the system. Important thing to remember is that in this Copenhagen interpretation, a system stops being a superposition of states, becomes one or the other when an observation takes place. That was the feeling back at that time, and in point of fact, it is not held by some quantum theorists today. Same time, 1928, Paul Dirac extended quantum mechanics for relativistic behavior. He also predicted antimatter, and he gave the foundation for for quantum field theory. Also, a few years after that, we have Linus Pauling, who put chemistry onto a quantum mechanical basis. He showed the electron pair bond was the interaction of an unpaired electron on two adjacent atoms. He set up rules that the electron's spin had to be opposed, that each electron can be in one pair at a time, and the strongest bonds are made using electrons at the lowest possible energy levels. By the way, this is where the ball and stick model of chemical compounds comes from. The sticks representing the pair bonds between electrons and the balls representing the atoms. Okay, now there was still hope in coming up with some objections to quantum mechanics. There's the phenomena where particles become interconnected because the state of one influences the state of the other. It's supposed to do so instantly. And that, of course, is an affront to relativistic mechanics, which says that you can pass information from one place to another instantaneously. So Einstein, Podolsky, and Rosen in 1935 suggested that quantum mechanics might be a good statistical theory, but there was some underlying deterministic phenomena that was actually making things work. The quantum mechanics was not actually reality, but it was a good calculation tool. Schrodinger himself wasn't happy about the probabilistic nature of his own equation. So he came up with the thought experiment of the cat in a box to show how absurd it was. He wanted to show that you could have a situation where quantum mechanics says that a cat could be either alive or dead, uh, when in fact everyone knows that it either is definitely alive or definitely dead, despite what the wave equation says. Now, the odd thing that happened is that when he proposed this experiment, a lot of quantum physicists says, yes, that's exactly what happens. The cat is truly in a superposition, uh, and that's the real case of reality. Schrodinger was quite bitter about that. Years later, when he was teaching his own students, he said it was just so silly that people accepted this idea of a probabilistic reality. Of course, concerning the cat in the box, there were always possibilities they hadn't even considered. Um, you know, and I'm going to get into the many worlds possibility in the next couple slides. So, what were the other interpretations? Von Neumann said a conscious observer is needed. Now that's interesting because the idea is that now the universe was actually being generated by conscious people. Wigner initially went along with von Neumann, but then he thought about it and he realized, well, the observer themselves is going to be part of the probabilistic system. Bohr decided that it was irreversible processes that causes the collapse of wave functions. For example, in the case of the cat in the box, the fact that a Geiger counter is there is triggering the collapse. It's not about you opening the box and seeing what is going on. The Geiger counter did it. Of course, as we said, Einstein, Brodowski, and Rosen, they wanted hidden variables. Well, in 1964, Bell said that we can test that. It came up with the Bell inequality that allowed you to do a statistical test to show what was actually going on. And what the Bell inequality proved, as people got back to it in later years, is that you couldn't have hidden variables. We had three primary things that had to be true. Realism says that observers are not needed for the universe to exist. Determinism, that knowledge of the present determines the future and the past. Locality, no action at a distance. And I throw in a fourth, quantum mechanic completeness, that quantum mechanics is a true picture of the universe. The Bell test showed you cannot have all four of those together. One or more of them has to be violated. And that is a controversy that continues right to this very day. In our development of the history, we have to mention, of course, Feynman and electrodynamics. That was back in the 40s and the 50s. He developed the diagrams that simplified calculation. There was a problem in quantum electromagnetic where infinities would come up, but he basically showed that if you simply ignore the infinities till the end, they would cancel each other out. This is called renormalization, and allowed you to do some very good calculations. Quantum mechanics, is very successful in explaining many phenomena, such as electron conduction and other matters. Hugh Ebert came up with the idea of many worlds, and this was again to somehow get away from the idea that there is an actual collapse of the wave function. And the idea here is that when the wave function says that there is a superposition of different states, well, what it means is there are two separate universes, one with one state, one with the other. And this happens every time there is such a superposition. So if you think of superpositions as not just being cats in the boxes, but going right down to the fundamental particles and their movements, there is a huge number of universes all existing together in the bulk of existence, where anything that could happen has happened. And these days, we're trying to do quantum mechanics at large scales to see phenomena at human-sized scales. That's one of our problems with abstractions. We like to believe in particles and definite paths and so forth because we're accustomed to that in our particular scale of existence. It's always been interesting that human scale of life uh, is too small to be worried about relativity every day and too large to be worried about quantum mechanics every day. Uh, but nonetheless, those things are there. Um, so, people are working on these ideas, trying to show how quantum mechanics can be with us in our everyday life. Of course, we know it is because we have things that work with quantum mechanics.